Hi class. So for the ANOVA, there is a practice assignment. It's under in-class practice assignments. Once you're in that content area, you'll see it says analysis of variance. There are two files there. The first one has the data and the questions and everything. The second one has some tables that we would need for the critical values. When you open that Word document, you'll see something that looks like this. So Samuel thinks individuals who attend independent private schools, religious private schools, and public schools will show differences in measures of academic achievement. He expects that students at private schools may benefit from the smaller class size and college preparation courses. To see if these students are better prepared, he obtains SAT scores from students who attend public school, religious private schools, and independent private schools, and we're using numbers there to indicate which group they're in, and we'll see those numbers in the Excel sheet here in a moment. So the question is there a difference in SAT performance between these groups? And you're going to use an alpha of 0.05. We have the data, we have some columns for calculations out to the right, and those are places where you would do your deviations or square deviations. And then it walks you through state the alternative hypothesis. For the ANOVA, the alternative hypothesis is simply that there is a difference between the three groups. So basically that the mean for group 1, we'll just call it M1, is not equal, actually we can do it this way, so that somewhere between the difference between M1, M2, and M3, there is a difference, and thus it is going to be greater than 0. And so if there is a difference between these three means, then there should be, you could also say that M1 is not equal to M2, or M2 is not equal to M3. Basically, we don't know if M1 is different than M2 specifically, or M2 is different than M3. We know that somewhere between Group 1, Group 2, and Group 3 there is a difference if the test is significant. So for this we would do the ANOVA. In particular, we're doing a one-way between subjects ANOVA, or analysis of variance. Now we know it's one way because we only have one grouping variable, in this case the type of school that they attend. Each person is only in one school, right? So they didn't attend multiple types of schools, and so we are looking between subjects where each subject is in one group or the other. For our assumptions, the assumptions are going to be basically the same as the independent samples t-test, where we should have randomness, we should have independence, we should have normality. That is normality by group. So the scores for group 1 should be normally distributed, the scores for group 2 should be normally distributed, and the scores for group 3 should be normally distributed. The new part is also that the variance for group 1 compared to group 2 should be relatively equal. Group 2 to 3 should be relatively equal, and group 1 to 3 should be relatively equal. So the variances across these three groups should be relatively equal, and that's known as homogeneity of variance or equality of variance. The first two, independence and randomness, we could check and we could look at how did he collect the data, and we could read the question more carefully. I don't think it says anything about those here. The other two, we could look at graphs, we could look at Levine's test, and in SPSS it will give you those fairly readily. As a rough estimate, once we get the variance, we could compare variance for group 1 to group 2, for instance, and then we could see, is the ratio between them greater than 2? And we would only need to do that for the largest variance and the smallest variance. As long as the ratio of the largest variance divided by the smallest variance is less than 2, it would suggest that we have met that assumption of homogeneity of variance. For our criteria, that's going to come from our table. And so if you look in here, we would get that using this table. And to use this table, we need two pieces of information. Well, really three pieces of information. We need our alpha level, which is 0.05. All of the light-faced are going to be those 0.05 alpha level, whereas the bold-faced that are right below them would be for 0.01 alpha level. And then we need degrees of freedom, but we need now 2 degrees of freedom. We need the degrees of freedom for the numerator and the denominator, or if you're connecting this with the prior video, the degrees of freedom for the between subjects and within subjects, where between subjects is going to be our numerator and within subjects is going to be our denominator. And you can think about how we calculate F. So F is mean squares between divided by mean squares within. So our numerator is between, our denominator is within. So our between is 3 minus 1, so k minus 1 is 2. And then if we look at the data, we have a total of, if you count those, 15 individuals. So we have n minus k degrees of freedom. So we're going to have 15 minus 3, which is going to give us 12. So on 2 and 12 degrees of freedom, our critical value is going to be 3.88. And at that point, we can switch over to the Excel sheet. And in fact, I've already put that information in here from that table. But now you know how to use that table and where that information is coming from. So looking in the sheet, I basically copied over this data. So this is exactly what was in there. And you've seen us do deviations and square deviations before. Now we have 3 sources of variability. We talked about this in the first video, where we have sum of squares between, sum of squares within, and then sum of squares total. Sum of squares total is very similar to what we've done before. So if you look at that, I'm taking the individual score, B2 in this case. I am subtracting the grand mean. And before, we only calculated the grand mean. It was the average of all the scores. So that's basically exactly what we've been doing before. And then we're going to square that. And so then the next cell, same idea, except now B3, how far is that? How much does that deviate from the grand mean? And square it. These other 2, within and between, those are new. Sum of squares within is going to be based on the square deviations within. So when we look at within, what we're looking at is the deviation of an individual, so B2 or B3 or B4, from the appropriate group mean. So we will have to make adjustments. We can't just do it once and copy and paste all the way down, because for the first 5 people, the group mean is 500. It's at H3. But when we get to person 6, right, who's on row 7, when we get to that person, they are part of a different group. They're all part of group 2. And so because of that, we now want to say how far is the individual from the mean for group 2, which is at H9. And then when we get to the third group, we once again are going to shift to the mean for group 3, which is at H10. And so when we look at group 3, it's going to be the individual score minus H10. And so I showed you visually how we did this in the last video, but here you can see numerically what are we doing. Well, we're just subtracting the individual score x1, x2, x3 from the appropriate group mean, and we know which group mean is appropriate based on this information over in that group column. The last piece is sum of squares between. You'll notice that there's a pattern. The first 5 scores all have the same square deviation between, because it's their group mean, and the group mean is the same for everybody in group 1, minus the grand mean, and then we square it. And then when we get to group 2, then it changes, but it's still the same from person 6 all the way down to person 10, because their group mean is the same for each person in that group. So we're going to take the group mean, which is at H9, and then subtract H7 from it, and we're going to square that deviation. And then last, we are going to take the mean for group 3, and for the last 5 people who are in that group, we're going to use that group, subtract the grand mean, the overall mean, and square that deviation, square that difference too. So we have all those, and then we can add them together. So this is where we're summing them. So this first one is the sum of squares total. So that is the total amount of square deviations between each person and the grand mean of 541.33. And so we add those all together and we get 49,373.33. For sum of squares between, again, we're going to sum the E column. And then for sum of squares within, we're going to sum that D column. The reason that I have them in this order with between over within is because eventually when I do the F obtained, the F ratio, it's going to be sum of squares or mean squares between divided by mean squares within. So to me it makes more sense that the numerator should come first or be above what will eventually be the denominator. I can check that I calculated these all correctly, or at least get a sense if I calculated them correctly, by adding together between and within. So here I have H7 plus H8, and actually now that I've made some tweaks, it should be H12 plus H13. And I see that if I add H12 plus H13, which is the between and within, I get the total. And by calculating this column separately, it gives me a way of checking. If those aren't equal to each other, I've probably done something wrong. And similar to the way that we know that there should be things that equal, it doesn't guarantee that I've done it right if they are equal, but if they don't equal, it guarantees that I've probably done something wrong. With between and within degrees of freedom, so the between is going to be k minus 1, and then within is going to be n minus k. So H2 is the total number of individuals. Sorry, these are, again, I made some adjustments. So H5 minus H6. Where H5 is n and H6 is k. For mean squares between, it's simply the sum of squares between divided by degrees of freedom between. And then for mean squares within, it's going to be the sum of squares within divided by degrees of freedom within. Finally, for the F obtained, or the F ratio, we're going to have mean squares between divided by the mean squares within, and we should see that that gives us 2.72 as the F obtained. Importantly, this F obtained is closer to 0. It is less extreme than the F critical, thus we would fail to reject the null. So at this point, if the omnibus test fails, we actually wouldn't even do the post-hoc test. However, for sake of practice, we will go ahead and do the post-hoc test this time. Additionally, it's a good time to point out that technically, given Samuel's hypothesis, we would have actually preferred to just do an independent samples t-test. So he first says individuals who attend these schools will show differences. That would suggest that there's a difference somewhere between these three schools. But then more explicitly, more narrowly, he says that he expects students at private schools as a group. He does not distinguish between religious private schools and independent private schools. He just says private schools. So it would actually possibly be more appropriate, given his way that he's worded this, to combine groups 2 and group 3 into one larger group and then do an independent samples t-test. And if you do that, and you have all the skills you would need to do that, you would actually find that the independent samples t-test from this data, by combining groups 2 and groups 3, is actually significant. So if we compare group 1 to the combined religious and independent private, you do in fact find that there's a significant difference and they actually do perform a little bit better. By the way, this data is made up. I don't know that private schools students are actually performing better, but you would find that in this data. So for the post hoc test, we have to calculate the error. In this case, the error is actually going to be the same in each case because, importantly, our sample sizes are equal across all three groups. So we wouldn't actually have to do this 3 times in this case. However, for your purposes, I would recommend that you make your notes kind of like this, because that will remind you when n isn't equal, how should you do this. And also, because n is equal, there's actually a simpler formula. I'm not going to have you learn both, because this formula will give you the same value, and it will also work when n is not equal. So here we take the square root of the mean squares within, we divide that by 2, we multiply that by 1 over the n for group 1 and 1 over the n for group 2, multiply that sum of those two quotients by mean squares within divided by 2, and then take the square root of the whole thing, and that gives us 23.80. And as I mentioned, it's going to be equal in this case because n is equal for all three groups. If the n was different, then this error term would be different. We then take that error term and it's going to become our denominator, and our numerator, very much like the t-test, is going to be the difference between group 1 and group 2, or group 1 and group 3, whichever groups we're comparing, contrasting, divided by that error term, whatever the error term is that's appropriate. So in this first HSD 1 minus 2, we're comparing group 1 to group 2, and we see that 500 minus 546 divided by our standard error, which is 23.8, is going to give us negative 1.93. We could flip this sign. It would simply involve comparing group 2 to group 1 instead of group 1 to group 2. So we would flip H9 to H8. And then we do that same thing when we compare group 1 to group 3. It's simply the mean for group 1 minus the mean for group 2, and then we divide by the appropriate error term. And then we would do the same thing for group 2 versus group 3. So we do all pairwise comparisons here. To see if that's significant, in that same table, and this table is also in your handouts as well, in case you need it at a later time, we can look and see that it says DF error, degrees of freedom error. Again, that's going to be your degrees of freedom within, or your degrees of freedom denominator. Unfortunately, even SPATS uses 2 terms for that. The good news for you is you're going to be informed about the different ways that this is called within the literature. I do apologize if it's a bit confusing at first, but he even mixes the 2 together and uses them interchangeably. So degrees of freedom for error is going to be 12, right? So n minus k. This is not actually degrees of freedom. If you look, it's the number of levels of the independent variable. So our independent variable in this case is the type of school, so there's 3. So on 3 and 12, our cutoff is 5.05, and we find that none of those exceed 5.05 in absolute terms. Again, we could easily flip the signs, and this is a non-directional test because it's a post-hoc test, and so because of that we end up using it's non-directional anyway. So the positive negative really doesn't matter. It just, in regards to absolute magnitude, is there a difference? And in this case we don't exceed 5.05, which is not surprising. We already didn't have significance in the omnibus test.